For those that are on, thanks for joining. My name's Tom with Rayco. Here we have Barry Landash with Siemens Industries, going to kind of walk us through continuous gas analyzers. We're calling it Processes 101. So without further ado, pass it over to Barry, let him do his thing, and the floor is yours, Barry.
Well, thank you very much, Tom. I do appreciate that. Good morning, everybody. My name is Barry. Is a channel partner manager and technical support for the Western region. Having said that, I act as a intermediary between the customers and Siemens and the channel partners and help resolve problems, make sure the applications are correct for the analyzer, assist customers in understanding their applications, their technical aspects, analyzers, make sure that everything is correct when the analyzer. The topic of today's presentation is the Analyzers 101. This is not necessarily a technical presentation per se. Meaning about detectors, the way analyzers work, and so forth. The Analyzers 101 is really a presentation to understand why analyzers are necessary, how to go about finding out what information is necessary, and how to correctly place the analyzers in the process, your process, or however you want to use them. That is one of the most critical aspects that many people tend to overlook, is finding out how and why and what to do with the analysis. The second part of this presentation is covered in much more detail. It's a technical seminar that spans about 8 hours or so. It can go longer and it can go a little shorter, but of course all those aspects are not covered as necessary. So anyway, thank you for joining. We do appreciate it. If you have any questions, please feel free to go ahead and speak up. Your phone's not on mute. And speaking of a phone being on mute, if there's any one of you that has a lot of background noise, we'd appreciate it if you put your phone or system on mute. We appreciate it. Thank you very much. When we get started, the most important thing is to understand what the parts of the analyzer are, because as you go through specifying the process or the project, it really helps to understand what the parts of the analyzers are and understand the acronyms that go along with it. Of course, the analyzer itself is the instrument that performs the task. It is much different than the name of an instrument. An instrument is something a little different. In the analytical world, an instrument is very similar to a thermometer or a barometer, or say a yardstick or a ruler or something like that. That is considered an instrument that most anybody can pick up and use. Analyzer is something that requires some level of skill for use. The sample system is a group of mechanical devices that takes the sample and puts it in a form so that the analyzer can read it. Many times the sample system is just totally overlooked, and many people think, well, you take a gas out of a process pipe and the analyzer can read it. Well, sometimes that's true. Most often it is not. It is very important to understand the parts of the sample system, what their functions, and how they can correctly deliver the gas to the analyzer. The sample point is the actual location for removing the process gas or liquid from the process. Defining the sample point is very important to understand how to get the process gas from point A to point B. The transport tubing is the actual transport mechanical device. That can be stainless tubing, that can be copper tubing, that could be Tygon, Teflon, just about anything that can withstand the pressure in the process from getting the sample from the sample point to the analyzer itself. The sample conditioning system is a group of mechanical devices that actually conditions and cleans up the sample to present it to the analyzer. The sample conditioning system, transport tubing, sample point, and analyzer is all part of the analyzer system. One of the things that many people overlook in finding the system is the recording device or the electronic devices that actually send the data to a PLC, a recording device, computer, or a distributed control system or whatnot. Screen. I-39 south is on the left, and then the freeway. For some reason I cannot advance screens.
Proceed on I-39 south.
Pardon me. There are different types and flavors and even colors of sample systems. You could have something in a Hoffman box, very similar to what's in the upper left-hand corner, or you could have a very large panel, 7 feet, 8 feet tall, 10, 12, 14 feet wide, as in the upper right-hand corner. The black box that's in the middle of the screen or the middle of the two rows of sample systems is an example of a conditioning system or a conditioner. That is actually a refrigeration device where the sample comes in, it's chilled, the dew point is adjusted, the water drops out, and then once the sample leaves the chiller, the temperature is raised. This is one of the ways to condition the sample. The lower right-hand corner is a very simple system where your sample comes in from a point of some sort. You could have a simple filtration or coalescer. Water's dropped out, and there's a gas pump that sends a sample to the analyzer. So the point of this is that the sample system is not necessarily a very complex and ominous device. It could be as simple as a filter, or it could be placed in a cabinet. It's just a whole group of things that can go into an analyzer system. So the question becomes, you want an analyzer. The understanding of analysis needs to be defined. You have to understand the reasons to install an analyzer. What is the reason? Is it safety related? Is it process control? Is it simply for information? Is it regulatory? Or is it just because somebody wants to put an analytical device on a stream and see what happens? Defining the reason is very, very important. And around that reason, there's criteria that really should be investigated and explored. And it's best to put those reasons down on paper. As far as installing the analyzer, how much money is in the budget? Is cheaper better? Not necessarily. Chances are, if the cheap route is chosen, usually the system will work somewhat, and that's a definite maybe. Chances are there's going to be a considerable amount of money wasted not only purchasing the machine, but the total install cost, meaning the operation cost after the machine is installed. On the other end of the scale is buying everything on the list necessary. Well, overkill is, yeah, you'll probably get everything that you want, and it'll probably be a good system. But again, you want to point toward a cost-effective system so that you don't waste money. Chances are many of the things on the list is not necessarily needed. So consequently, if you define the parameters of what you want, usually including the understanding of expectations and the criticalities of the information that you want, is the path of best taken. Another part of defining the reasons and defining analysis is understanding the process. This is where many people go wrong. To define the process, it's commonly thought of the process is what's in the pipe, so to speak. For instance, if there's a refinery or people are talking about a refinery, the process is typically understood to be what is in the tower, what is in the exchanger, what is in the pump, what is in whatever device you want to measure. And that's not necessarily the case. The process is the operation of what you want to analyze, or the gas or the liquid of what you want to analyze. But understanding the process of automation, the process of transporting the sample from the point through the data collection is very, very important. And understand what happens from point A to point B is absolutely critical. The questions that I have on the screen, what's in the process, and are you sure you know, is the questions that always needs to be in the back of people's minds when they trying to understand what that process is. Is the phases of the gas or the process is a gas? Is it a liquid? Is it a combination of both? What's the solid content? Do you have submicron particles? Do you have micron particles, rocks, boulders? What's in that gas or liquid? What about the hazards and safety of the process? Is it flammable? Is it reactive? Is it caustic? Is it acidic? Is it sticky, so to speak? Does it stick to the metals or the components? And the list goes on and on. What are the temperatures, pressures, flows, and dew points of the sample? Knowing the pressures and the temperatures and dew points are critical when it comes to understanding the process of the sample conditioning system. And I cover the sample conditioning systems in quite a bit of detail in the extended version. We talked a little bit about the physical attributes. Is it corrosive, reactive, sticky, and so forth. The second part of understanding the need for an analyzer is defining the expectations. What do you want it to do? How's the data read? Is the data stored? Is it used? How is it used? The online time of the analyzer. How long can a person go or the system go when the analyzer's down? What happens during maintenance? What happens say in the case of environmental analysis, where if an extended downtime is incurred, are there any fines? How much does it cost to actually run the analyzer? What's the maintenance time? The list goes on and on and on about the total installed cost and defining those expectations. Another critical part is defining and thoroughly understanding where to take the sample for analysis. You want to take it on the suction of a pump, as an example. Do you want to take it on a discharge of a pump? What's the flow rates? What's the pressures? Are specifications exceeded for the analyzer and so forth? So once you define all those things, okay, so now what? Where do you go? You got all this list of expectations, you got the definitions, you got the process on a paper. So now where to go? What comes first? The sample system or the analyzer? I call this the chicken or the egg syndrome. What comes first? The chicken or the egg? Want to say, okay, I need XYZ analyzer, or I want to measure a certain process? Unfortunately, the answer is not very simple. It's very complex. Typically, when a person or a company goes down to specify an analyzer, it's typically understood that you want an analyzer, but you usually don't know what or where you want to put it. And defining all those things help identify the type of analyzer, the detector, the technology of the machine, the reasons, the budgets, the criticality, and expectations typically will help make those choices. The components of analysis can really narrow down your choices for your analyzer very, very quickly. The different types of detectors will usually steer a person in the right direction, or steer a specialist like myself in the voice of analyzers. As an example, if say you want to measure oxygen in a furnace for process control, there are a multitude of analyzers that can be chosen. Right off the bat, use zirconium oxide technology. You can use paramagnetic. You can even use a gas chromatograph. You can use mass spec. Tons of analyzers that are available. However, if you say you want to make it a safety critical analyzer where speed is the most critical part of your system, then the choices are narrowed down considerably, and typically that is pointed toward tuned diode lasers or laser technology, because the response time is so fast. So the process actually shapes what's needed in the analyzer. Liquid, gas, solid, dew point, and so forth. That will point toward not only the analyzer but the sample system as well. Usually one of two paths defines what comes first. The type of sample that's desired, or the type of analyzer needed or wanted. For example, in a smaller facility where, say, maintenance is, say, either by contract or, say, by people who are not familiar with the physics and chemistry of analytical equipment. Typically, you want to make the choice of less complex analyzers, and typically go with sensors rather than a complex analyzer system. On the other hand, if the analyzer is to be placed in a large refinery, usually the technical expertise is much higher. There's usually specialists and engineers that are capable of maintaining that equipment. So it's understanding what the expectations are and where the analyzer will be placed. If those on the call are familiar with the fire triad, where the heat, fuel, and oxygen come together to make a fire, I've come up with a triad for an analyzer system. The analyzer success, or the installation success of the analyzer system, is typically a 3-point triad. There are 3 things that are absolutely necessary to have a successful installation, and without those 3 things, usually the costs go up and the success is not as great as it should be. The first thing is the sample system. Understanding what is necessary for the sample system correctly, identifying all the parts, understanding dew points, pressures, and so forth is absolutely critical. The second thing is the process. Understanding the process is the other critical thing, the second critical part, and that process has to do with the actual chemical compounds that is in a pipe or is in the process of the customer's system, whether it be a refinery, a digester, or any type of process that the customer wants to monitor. Again, that process has to do with the actual facility, the manufacturing facility, all the way through the analyzer's output. So the entire process covers the analyzer system, transport tubing, and actual chemical makeup of the system itself. The technology rounds out the triad. Understanding the technology that's available is the third critical part. How does the analyzer system actually read the sample? How is that sample analyzed? How is it broken up? What happens inside the device itself? How the sample system makes the sample or filters the sample to present it to the analyzer in an appropriate manner. All those things are in the technology part of the triad for analyzer success. Removing any one of those 3 parts of the pyramid, the analyzer success is, may be somewhat questionable, or may not meet expectations, or may not give the desired results. Moving on to the individual parts, the sample system is where most of the problems usually occur. More than 80% of the problems in an analyzer system usually is pointed toward the sample system for some reason. Having said that, the sample system's job is to provide the process and the actual gas or the liquid or whatever you want to measure to the analyzer. It must be compatible. The sample system should not be reactive. It's got to be very timely. It's got to provide an acceptable delay from real time. It's got to be representative. It can't change the original sample. For instance, if you're measuring, say, water analysis and you want to measure the pH, well, the sample system should not change the pH of the water. You can't have something adding, say, an acid or a caustic to the water if you want to measure the sample system. Or if those components are somewhat reactive and change the sample itself, it will not be representative. Reliable. The KISS attitude works very well. It's got to be simple. It's got to be easy to repair, and you have to be able to get to it to change the parts, to change the filters or whatnot. It's got to be cost effective, meaning you need to know the dollars and the benefits of the system. And of course, really it should be, the safety of the system should be number one. It should not harm the user or environment. All those things go into the correct sample system design. So it is very critical to have the correct sample system on the process to deliver the process appropriately to the analyzer itself. Understanding the details of the entire process is critical. It is also critical to know the delay time from the very point of the sample entering in the sample transport tubing to the measuring output of the analyzer. What is that delay time? For instance, this has a lot to do with the sample system itself and time delay that I mentioned before. It has to be timely. For instance, knowing where to take the sample point has to be calculated into the overall analysis. As an example, if there's a large tower with a pipe coming into the bottom and going out the top, and let's just say this tower is 20 feet in diameter and say 100 feet tall, the residence time inside that tower is very long. So taking a sample on the side of the tower is not very advantageous. True, you're taking the sample of the tower and you're getting a what is thought to be a timely sample, but the residence time inside the tower is a factor of the analysis. The best place to take that sample would be either on the inlet or the outlet, depending upon what's going into the tower. That way you get a better residence time and understanding of what the tower is actually doing, either before the process makes changes, as on the inlet on the bottom, or on the top after the reaction takes place. Separating the information of the analysis of the process between nice to know and must have and what falls in between. And of course, how will the analytical data be used? Will it be recorded? Will it be written down on paper, automatically recorded in a PLC, or sent to the distributed control system, or somebody's just actually sitting in front of the unit watching the dial? Knowing the technology and the types of detectors and what their limitations are is a very large part of how the analyzer goes in. What is the best method for reading that particular component? Would it be an infrared detector, a flame ionization detector, a thermistor type detector, gas chromatograph, lasers, or oxide? All those things are critical into understanding the technology of the heart of the analyzer. In the extended course, I talk a lot about the nice-to-know stuff and the must-have stuff and the technology and how the two compare. Understanding the technology really limits or narrows down the type of analyzer that can be installed in the system. Defining the use of data can provide hints of the type of technology that's going to be used. If you need something very fast, a response very, very fast, as in on the order of a second or less, then laser technology is usually the best choice. If you can withstand minutes of delay, typically you want a traditional extractive system where you can condition and withdraw the sample. Defining the use of the data can help provide a direction for the process control, safety, or information, and that goes into understanding the expectations of the system. And also the stability of the system. What is the best technology for the process? I have written down on this slide apparent stability and real stability. And that they're on opposite ends of the scale, and the stability is covered more in the advanced technology course. Understanding the reasons for analysis. What comes first, the analyzer or the sample system? We've been talking a good bit about that. Understanding the phases, solid content, hazards and safety issues, the physical attributes, the solubility, the dew points, all that goes into what's understanding in the process. The type of analysis that's needed. Is it regulatory? Is it safety? Is it advanced computer control, or is it manual adjustments? Is it information only? Understanding the cost savings for the analysis. That usually drives the project. Understanding how much that analyzer system will make for the company or the customer or wherever it's going to be placed is the key. For example, in an advanced process control system, if a process, by controlling a certain variable or certain component, say by 5%, will provide, say, $100,000 in savings for the process, $100,000 per month, versus information only. What drives the information only and making the cost benefits for the analyzer itself? Sure, it's nice to have, but how much is that actually going to make for the process savings? The analyzer system has got to be compatible. The compatible system will not harm the analyzer nor prevent it from producing a reliable analytical result. And these are some questions that need to be asked. Is the analyzer system compatible with the process? Have all the operating process conditions been explored? What's the minimum? What's the maximum? What's stagnant? What's maximum? What about an upset condition? If it's a gas system, will liquid be put to the analyzer? What safeguards are put into the analyzer system to prevent liquid actually getting to a gas analyzer and destroying it, or vice versa? What about solid content? Anything that is reactive in the process? and so forth. What are the operating anomalies that may harm the system? Talking a little bit about upset conditions. What about changing process? Like, for instance, if it's a chemical process, is there a changing of the desired component that you're trying to analyze, is that going on in the sample system while you're trying to measure it? I had the opportunity to work in a chemical plant one time, and it was a plastics plant. An analyzer system was put in where the reaction was taking place inside the transport tubing that was continuing on from the tower of desired analysis. It was extremely difficult to understand how that process control could be placed on the system when the reaction was taking place inside the transport tubing. So understanding the compatibility is absolutely critical. Timely. Talked a little bit about delay time. The delay is calculated from the very tip of where the sample goes into the transport tubing to when the analyzer reports its result. All delay is inevitable, and it's all additive, but the system should be engineered to minimize that delay. The question's asked: what are the time requirements of the analysis? What are the time delays? And again, all delays are additive. What is acceptable? Has to be representative. It's got to be accurate. It's got to provide a meaningful analytical result for the intended purpose. These are the questions. What is a useful result? What are the requirements of the results? Is it regulatory? Is it safety driven? Is it information only, process control, and so forth? An analyzer system has to be reliable. Keeping it simple is usually the best way to go. It's got to be easy to repair. For instance, if you put an analyzer system in a Hoffman box, can you get at all the parts? Do you have to dismantle everything to get to the parts? One of the things I do is repair my own cars. Many of the popular cars nowadays makes it so difficult to do something as simple as change the oil or change the spark plugs. You got to dismantle half the motor just to get to the parts. It's very aggravating. So in the consideration of an analyzer system, those are some of the things to look for. One of the most important things about the reliability of the sample system and the analyzer system, do the operators believe it? Can it be trusted? Is it the right analysis? It's very, very important. Cost effectiveness. Know the benefits of the system. What are the labor costs? What are the spare parts, consumables? What are the utilities? What about wasted or recycled process? Where is that process that's analyzed going? You put it back to the process, or do you put it to the US of A? All those things are very important. Lost opportunities. Lost opportunities point towards the people that have to work on the system. If they have to work on the system all the time, what are they not doing while they're working on the analyzer? So if the system is not put in correctly, as in, say, the dew points aren't identified prior to installation and liquid gets in the analyzer, that causes a lot of maintenance issues. The maintenance people work on the analyzers, and then what are they not doing while they're working on the analyzer. Those are lost opportunities. Those things need to be identified as well. And of course, the process downtime. The cost effectiveness comes down to really one question: what is the most simple, easy to maintain, and cost-effective design that will provide an analysis that operators will believe? Understanding all the above and the cost involved in installing the analyzer is critical to understand how much will that analyzer actually cost for total installation. Safe. It's got to be safe. All plant safety procedures apply, then some. What I mean by plant, it's either refinery, chemical plant, wastewater treatment plant, engineering company, lab, whatever. All those safety procedures need to be followed. And the question that needs to be asked is every component in the system safe? One of the things that are often overlooked is the pressure of the sample being placed on the analyzer itself. What safeguards are there to prevent overpressuring of the analyzer? Do you have safety reliefs? Do you have pressure relief devices? Do you have rupture discs? And the list goes on to make sure that you have a safe system. Of course, getting the right answer is most important. The focus of an analyzer system should be compatible sample, making sure it's timely, representative, and keeping everybody safe. Just making sure you get the right answer. And of course, be aware of the dreaded composition change. Haven't talked about this very much, but the composition change has to do with changing of a gas at standard operating temperature and pressure, where it's at equilibrium. If you change those pressures or temperatures or whatnot, the composition of the gas will change. Either it will get drier, or conversely, it will form a liquid, and that is one of the the worst thing that can happen to an analyzer system, where you get water in a gas analyzer. Totally destroys the machine. That concludes the Analyzers 101 in getting the right analyzer into the system. Those are the questions. Those are general questions. Again, each one of those topics are explored in quite a bit of detail, and then some, in the advanced course. And I'll be more than happy to schedule that and explore the scheduling and the opportunity that we can provide to give you a better understanding of analyzers as well as the technology. I would like to thank RACO and all the folks at RACO for helping put this on. And if anybody has any questions, I will take those now.
Yeah, thanks a lot, Barry. Yeah, I got everyone off mute if you want to ask a question. There's also a chat box if you want to type in a question as well. And if you can't think of any questions now, you know, send us an email. We'll definitely follow up with you.
Oh, it doesn't look like anybody has any questions.
No, it doesn't look like we have anything. Well, if that's the case, we'll, you know, thanks to all that have attended. We're going to make a recording of this available on our website, on raco.com, in our training session, or in our training page. Again, if you have any other questions, concerns, let us know. Possibly a copy of the presentation. Yes, yeah, we have a recording of the full presentation, and we're going to render it. We'll probably have it available by the end of the week. So can either email it to you if you like, or we're going to try to get up on our web page as quickly as possible.
And Tom, I'll get you a copy of the presentation, a PDF copy, to send out to all those who would like it and so forth.
Okay.
What I'll do, I'm typing my email address to those out there. If anybody has any questions, you can email me at that email address, having to do with analyzers in general or specific. I'll be happy to answer your questions. If there's any projects that you may have that you're looking for analyzers, Siemens does have a large portfolio of solutions. Again, a lot of those solutions are discussed in the advanced course. There's not enough time to discuss them here within an hour or so to discuss those. But I'll be more than happy to help anybody with the technology behind it, understanding what's necessary for analysis and so forth. So please email me or contact me. I'll be more than happy to provide you with either direction or get somebody on the phone and put you in contact with somebody else.
Sounds good. We appreciate it, Barry.
Sure.
Thanks again for doing this for us, Barry, and those that have been in attendance, thank you. Like Barry said, if you have any questions, you can send anything to him. You can also send info to us at RACO. My email address is tom@raco.com. And with that, hope you all have a great day.
Okay. Thank you very much, Tom. I'll talk to you soon.
All right. Sounds good. Take care.